is the video for 4.2 Day 2. It's the second day on implicit differentiation. So the warm-ups are here. I want you to pause the video, try at least 1 and 2. 3 has a lot of algebra to it, but you can do it. You have all the skills. Pause the video, come back when you're done. If you're back, that means you tried all these. So this is the key to the warm-ups as far as what your final answers would be. And then if you need to look in more detail, pause the video and look at the actual work that I've got here so that you can find out how you're doing on your implicit differentiation and using it to find slopes and y prime values. So we want to add some more stuff in with that today, just double check, do some finer points of this. In this section, when you do the reading, they finally bring up the power rule for rational powers. We've been using it all along. Rational powers meaning powers that aren't always whole numbers, they could be fractions. So we've been replacing and using x as 1/2 when we're representing square root of x in derivatives. This is finally when the book brings it in and says there is the rule and that you can use that. So the rule itself isn't new, but the fine print is what we want to be careful about, because when we use it and we say that there's a derivative of this square root function, there is one place where that derivative won't exist. If the power that we're using is less than 1, meaning the power that we start from is 1/2, 1/3, something that is smaller than 1, when we actually do the derivative, even if that power is negative when we start, the derivative takes the power down by a whole number and it takes it into negative territory then. So what the derivative is equivalent to, if we rewrote this, is this, and the fine print says that when we do that, we start in our original function with a power that's less than 1, our derivative ends up with a power that's negative, and therefore at x equals 0, this derivative does not exist. So we need to keep in mind that this is not differentiable at x equals 0 once the derivative has a power that's less than 1, or less than 0. Okay. So if the power that we start with is less than 1, then the derivative does not exist when x is 0, and we just need to keep that in mind. So when we evaluate that, we realize it would cause the denominator to be undefined. So here's where we're going. They're going to use what you know about differentiating on both sides and doing this implicit differentiation to solve the same kind of problems you've been doing before. So find the point or points on the curve where the tangent line's parallel to the x-axis. Parallel to the x-axis right away tells me I'm looking for lines whose slopes would be 0. So I'm looking for tangent lines to points on the curve whose slopes would be 0. So to find out whose slopes would be 0, I need to basically find where my derivative, or the rate of change at that particular point, is 0. So if you want to pause the video and get your derivative, if not, we'll walk through it. So derivative-wise, we're going to do implicit differentiation, differentiate on both sides with respect to x. So x squared's derivative, 2x. 2y squared's derivative, we need to think chain rule as a 4. Y to the first power times whatever y's derivative is. 4's derivative is 0. 2xy, we're going to use product rules, so we're going to be equal to twice the derivative that comes from xy, derivative of the first times the second, plus first function times derivative of the second. That one comes up often, so you'll probably get used to doing that. I'm going to distribute on this side. Bring this side down. The general idea then is gather all my terms that have a dy dx on one side so that I can take that out. So on this side I'm going to do it in one step. Feel free to gather them first on one side and then factor them separately. On this side there already is a 4y term. I'd be bringing this term over to the left-hand side to join them. This 2y is still here. I'd be bringing this one over to join it since it doesn't have the dy dx. At that point then I want to divide and get my derivative. So derivative with respect to x is going to be, and I'm going to factor a 2 out of this right away as I write it because I'm noticing that everything I've got has got that. So when I divide both sides by that 4y minus 2x, I notice that factor of 2, so my derivative is y minus x all over 2y minus x. So that's my derivative, but they would like to know all the places that that would have a slope of 0. So where on the curve we'd be at 0. So I want to set that equal to 0. Anytime a fraction's equal to 0, the only way to get it equal to 0, if you think about cross products, I'd multiply the denominator by the 0, is to get that numerator to be 0. So when will y minus x be 0? When y's and x's are equal. And you'd say, well, when is that? So when on the curve of that original function are y's equal to x's. So our original function up here, to figure out when y's are equal to x's, one way we can do that is to actually set y equal to x in there. So instead of x squared plus 2y squared, I'm going to find all the places where the x value and the y value are equal by saying 2x squareds plus, equals 4 plus 2 instead of x times y. If they're equal, that would be 4x squared. I could also replace them all with y's and find the y values first. So on this side, I have 3x squareds. And I could also solve this with my calc as long as I left my solutions, my original equation and my solution. So I know that the x will equal the y value on this graph when x is 2 and when x is negative 2. There will be 2 different times. To find the y value, I could plug the x back in, but here's the other thing. I know I was looking for places where the x and the y value are equal. So if x is 2, y is 2. If x is negative 2, then y is negative 2. So the 2 places on the graph where these would be equal to 0, the slopes would be where their x's and their y's are equal. And those 2 points would be 2, 2, and negative 2, negative 2. I'm going to take this off so you can actually see what that looks like on the graph. And the graph of this, and I did this on Desmos, the graph of this is this nice kind of ellipse type looking thing. And if you look at positive 2, you can say, oh yeah, that looks like I should have a slope to that tangent that's parallel to the x-axis. And again, at negative 2, you can confirm and say, that looks okay. All right, second derivative here. So second derivative, we're going to have to find the first and then get the second derivative. So first derivative is going to be my plan of attack here. So 2y dy dx plus 2 dy dx equals 2. I do need to clean this up so that I have an actual first derivative. So my first derivative in this case is going to be 2 divided by 2y plus 2. Notice how x's dropped out there. I don't even have x's in my expression. Dividing both numerator and denominator by 2 or factoring a 2 out, that's what dy dx is worth. We need to keep this in mind when we do the second derivative because dy dx is going to show up in the second derivative. So when I go to take the derivative of 1 over y plus 1, I need to be thinking about the fact that that's going to be a quotient rule situation. So I'm now finding the second derivative with respect to x. So I'm going to go back to what I just found, 1 over y plus 1. I'm going to evaluate that derivative using some quotient rule. Low times d of high, derivative of high, minus high, derivative of the low is dy dx, or 1 dy dx, all over the denominator factor squared. This zeroes out, so in the numerator I am left with a negative 1 multiplied by the derivative of y with respect to x all over this. You say, well, what do I do? I can't just leave that. You don't, so we need to go back to the fact that we know what dy dx is. dy dx is 1 over y plus 1. So I can take that and substitute that in right here. So when I do that, I'd have negative 1 over y plus 1, all over y plus 1 quantity squared. And I can clean that up a little bit, and I should. So that's really a y plus 1 factor to the negative 1 in the numerator. And I have 2 factors of it in the denominator. That -1 factor of it really means it belongs in the denominator as a third factor of y plus 1. So there's our second derivative. So if dy dx comes up in a second derivative, you know what that is, and you're going to sub it in to find the derivative for the second part. All right, last one. They would like to know where the slope of the curve is defined. So slopes for curves would be undefined if we had a cusp, a corner, a vertical tangent. We're not going to look at the graph to tell, so we need to be able to find it derivative-wise. So we need to find dy dx for this and find out where dy dx is defined and isn't. So this is a use of your implicit differentiation. You can pause the video and try to get this one yourself. We've got a little bit of product rule going here. We also have a little bit of product rule going here, so when we differentiate on both sides, we're going to need to make sure that we do that carefully. On the other side, what's nice is we'll get a 0. So differentiating this first part by product rules, so derivative of the first term times the second, plus derivative of the second term times the first. So that's all coming from this, minus everything that comes from the next derivative of this next term. So derivative of the first times the second, plus derivative of the second, which is going to have a dy dx, times the first term, and it's equal to, and I can't squeeze that in there very well, 0 on the other side. So cleaning this up, I'd like to be able to gather all my dy dx's on one side and all my not dy dx's on the other side, but first I want to clean this up so I can see what I actually have. Squared dy dx, kind of hear the storm going in the background, minus a y squared minus 2xy dy dx equals 0. So I want to keep all my dy dx terms on one side and move everybody else to the other side. So I've got x squared minus 2xy. I want to add the y squared to the other side that doesn't need to stay here and subtract the 2xy term. So then I want to get my derivative. It's going to be what I already have on the other side, all over this, the x squared minus 2xy. So I need to see where this is not defined, because they asked me to tell all the places where my derivative is defined, so it'll be easier first to find where it's not defined. So it's not defined if my derivative's denominator is 0. So it would not be defined if x squared minus 2xy were equal to 0. So we want to see if we can find those places. We say, okay, how do I set this equal to 0 and solve? So I'm going to move this to the other side. No, I'm not. I'm going to factor. Sorry. So I'm going to factor out the x. Okay, so setting each factor to 0. If x is 0, the denominator is 0. If x minus 2y is 0, the denominator is 0, which means my x's are twice my y's, or my y's are half my x's. So when they ask where it's defined and where it's not, here's our derivative, and it's defined for all x's that are not 0, and for x's that are not worth twice their y value. I don't need to find each of those on the graph. I'm telling where in general that's going to be. And I was really specific about the x equals 0 part. That's an easy one. So this is in green, the graph of the original function, not the derivative, but the graph of the original function. And so when you see on the original function, this orange line isn't really part of the function. The green curve is. You can see that it's got basically an asymptote at x equals 0, so it makes sense that there's no derivative at x equals 0. The blue line that I put in is all the places where x is worth twice the y value, and you can see when it hits this part right here, this point exactly would be where we'd have a vertical tangent, and that wouldn't be able to exist either. So your practice assignment for 4.2 day 2 is here. Key is posted in the drive.